This is a video from section 2.2 in a linear algebra class. Let's take a look at problem 1. Suppose A is the matrix -2, 3, 1, 4. A transpose is the matrix -2, 1, 3, 4. The determinant of A is -2 times 4 minus 3 times 1. Well, that's -11. The determinant of A transpose is -2 times 4 minus 1 times 3. That's -11. And so we can conclude from this, or we have verified from this, that the determinant of A is the same as the determinant of A transpose. That's number 1. Let's take a look at number 2. A is the matrix -6, 1, 2, -2. A transpose is the matrix -6, 2, 1, -2. If I take the determinant of A, I get -6 times -2 minus 1 times 2. That's 12 minus 2, which is equal to 10. The determinant of A transpose is -6 times -2 minus 2 times 1. But that's 12 minus 2, and that's equal to 10. So therefore, we have verified that the determinant of A and the determinant of A transpose are the same. Let's take a look at number 3. So here, A is the matrix 2, -1, 3, 1, 2, 4, 5, -3, 6. A transpose is 2, 1, 5, -1, 2, -3, 3, 4, 6. Okay. So we got to get the determinant of A and the determinant of A transpose. So if I want the determinant of A, so we can expand about the first column of A. So if I look at the entry 2, I'm going to delete the row in the column that contains the 2 and then multiply by the determinant of 2, 4, -3, 6. I'm going to go -1 times, because the entry in the first column of A, the second entry, is a 1. If I delete the row in the column that contains that 1, I'm looking at the determinant of -1, 3, -3, 6. And then I'm going to go +5, right? So I'm going to look at this entry 5, and then delete the row in the column that contains the 5 and multiply by the determinant of -1, 3, 2, 4. So this is 2 times 12 minus a -12, which is 24, minus 1 times -6 plus 9 is 3, plus 5 times -4 minus 6 is -10. I hope that's okay. Well, 2 times 24 is 48. 48 minus 50 is negative 2. Negative 2 minus 3. This should turn into negative 5. Now, I want to look at A transpose. Now, let's remind ourselves. A transpose is the matrix 2, 1, 5, negative 1, 2, negative 3, and then 3, 4, 6. And then I'll expand. Now, I fully realize, right? I can expand around the first row of A transpose and basically get the same answer. But I'm going to expand around a different row or column and show that you're going to get the same answer regardless. Okay? So in other words, let's expand around the third column of A transpose and show that you're going to get the same thing. So I'll start with 3. Delete the row in the column that contains the 3, and I'm going to multiply by the determinant of 1, 5, 2, negative 3. Minus 4, right? So let's go to the next entry. Delete the row in the column that contains the 4, and multiply by the determinant of 2, 5, negative 1, negative 3. Plus 6, that's the next entry over. Delete the row in the column that contains the 6, and multiply by the determinant of 2, 1, negative 1, 2. So this is 3 times. That looks to be like negative 13 minus 4 times. Negative 6 minus a negative 5 is negative 1 plus 6 times. 4 minus a negative 1 is 5. So this is negative 39 plus 4 plus 30. It looks like that's negative 5, and we have thus verified that the determinant of A is exactly the same as the determinant of A transpose. That's number 3. Let's take a look at 5. A is the matrix 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, negative 5, 0, 0, 0, 0, 1. Now, A is an elementary matrix. A is also a diagonal matrix. So if I want the determinant of A, it's going to be the product of the entries along the main diagonal. So it's 1 times negative 5 times 1. Correct answer is negative 5. Let's take a look at 7. Suppose A is the matrix. It's 1, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 1. Okay. And I want to find the determinant of this matrix. So 1, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 1. Okay. I'm going to take row 2 and swap it with row 3. But when you do that, you end up changing the sign of the determinant. And so this is negative the determinant of 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. And then the correct answer here is negative 1 times 1 times 1 times 1, which is negative 1. Therefore, the determinant of A is negative 1. That's how we do number 7. Now, let's take a look at problem number 9. Now, I want to look at the determinant of 3, negative 6, 9, negative 2, 7, negative 2, 0, 1, 5. This one's a really good question. So we can use a combination of row operations and cofactor expansion to do this problem. So notice how the first row, in the first row, every entry has a factor of 3. So I'm going to pull a 3 out in front of the determinant and then write 1, negative 2, 3, negative 2, 7, negative 2, 0, 1, 5. Okay? Now, my goal is I want to put a 0 here using the first row, kind of like with regular row operations. So I'm going to take 2 row 1, add it to row 2, put the result back into row 2. When we do that, we still have the 3, and then I'm going to multiply by the determinant of 1, negative 2, 3. I'm going to put a 0 here, a 3 here, a 4 here. And that's the second row. In the third row, we get 0, 1, 5. Now, from here, I'm going to swap row 2 and row 3. Now, when you swap those, the sign of the determinant changes, okay? So this is going to be a negative 3 times the determinant of 1, negative 2, 3. That's the first row. Then we get 0, 1, 5 for the second row. And then 0, 3, 4 for the third row. I'm going to go negative 3, row 2, add it to row 3, put that result back into row 3. And then when we do that, we get negative 3 times the determinant of 1, negative 2, 3, 0, 1, 5, 0, 0, right? And then negative 11. I'm done. So we get negative 3 times 1 times 1 times negative 11, right? It's the product of the entries along the main diagonal, right? Because notice how you have a main diagonal. The entries below the main diagonal are all zeros. And so this is called we're looking at an upper triangular matrix. And so taking the determinant of an upper triangular matrix is very straightforward. Correct answer here is 33. And it's pretty nice. Let's take a look at 11. Suppose we have the determinant of 2, 1, 3, 1, 1, 0, 1, 1, 0, 2, 1, 0, 0, 1, 2, 3. So right off the get-go, I want to take row 1 and swap it with row 2. When I do that, I get the determinant of 1, 0, 1, 1, 2, 1, 3, 1, 0, 2, 1, 0, 0, 1, 2, 3. Okay? Now, if I take negative 2 row 1 added to row 2, put the result back into row 2, that's going to turn this entry here into a 0. And that's what I want, right? And so we get the determinant of 1, 0, 1, 1. Now, if we go to the second row, we get a 0, a 1, a 1, a negative 1. 0, a 1, a 1, a negative 1. And then the next two rows don't change. So we get a 0, 2, 1, 0, 0, 1, 2, 3. Like so. And remember, now by the way, now let's take a look. When we switch, right, the sign of the determinant changes. So I want a negative there, right? And then if we come back, there's a negative here. Now, I'm going to switch again. So I'm going to take row 3 and swap it with row 4. So I get the determinant of 1, 0, 1, 1, 0, 1, 1, negative 1, 0, 1, 2, 3, and then 0, 2, 1, 0. Okay. Now, I'm going to take negative 2 row 2, add it to row 4, put the result back into row 4. So we'll just do that first, because that's going to turn this entry into a 0, which is what you want. And so this is the determinant of 1, 0, 1, 1. 0, 1, 1, negative 1, right? So the first two rows don't change. And then we got 0, 1, 2, 3, 0, 1, 2, 3, and then 0, and then here I'm going to get a 0, and then I'm going to get a negative 1, and then I'm going to get a 2. Now, from here, I want to turn this entry into a 0. So I'm going to take negative row 2, add it to row 3, put that result back into row 3. When I do that, I get the determinant of 1, 0, 1, 1, 0, 1, 1, negative 1, 0, 0, 1, 4. And then 0, 0, negative 1, 2. And we're almost done, right? Because I get a 0 there, which is what I want. I get a 1, and then I get a 4, right? That's the third row. And then a 0, 0, negative 1, 2. Now, I need this to be a 0 because I'm turning this into an upper triangular matrix that I'm taking the determinant of. So I'm going to take row 3, add it to row 4, put that result back into row 4. So I'm just trying to get you guys comfortable working with 4x4 matrices. So we get 1, 0, 1, 1. 0, 1, 1, negative 1. So the first two rows don't change. Then I'm going to get 0, 0, 1, 4. And then 0, 0, 0, 6 should be the last of them, right? Because if I add up row 3 and row 4, I'm going to get a 0 here, I'm going to get a 6 here. So it looks like we're good to go. And so this is 1 times 1 times 1 times 6. Correct answer here is 6. And that's how you do problem number 11. Let's take a look at problem 13. Suppose we have the following determinant. So we have 1, 3, 1, 5, 3 for the first row. -2, -7, 0, -4, 2 for the second row. Okay? And we get 0, 0, 1, 0, 1 for the third row. And then we get 0, 0, 2, 1, 1 for the fourth row. And then we get 0, 0, 0, 1, 1 for the fifth row. Like this. And I want to give you guys some options here because this is a 5x5 and it starts to get big, right? I want to turn this entry into a 0 right off the get-go. So I'm going to take 2 row 1, add it to row 2, put that result back into row 2. So we're going to deal with a 5x5 temporarily. So this is 1, 3, 1, 5, 3 for the first row. 0. And then we get -1, 2, 6, and then I think that's 8 for the second row, right? And then 0, 0, 1, 0, 1 for the third. 0, 0, 2, 1, 1 for the fourth. 0, 0, 0, 1, 1 for the fifth. So right off the get-go, that's our determinant, right? Now, we can expand. So remember, we could use cofactor expansion, right? In other words, we can expand about the first column of this new determinant, right? And so we're looking at the determinant essentially of a 4x4. So we can, in other words, reduce this to a 4x4. And so it turns out I claim this is the determinant of -1, 2, 6, 8. That's the first row. The second row should be 0, 1, 0, 1. The third row is 0, 2, 1, 1. And then we get 0, 0, 1, 1. Okay? Because if we expand around the first column of this new matrix here to take the determinant, the rest of these entries are all zeros. So if we delete the row and the column that contains the 1, we're looking at the determinant of this submatrix right here. And that's what I have. Now, I'm going to pull a -1 out of the first row. And when I do, I get the determinant of 1, 2, -2, -6, -8. 0, 1, 0, 1, 0, 2, 1, 1, 0, 0, 1, 1. Now, I could make the same argument to you in that if I expand around the first column of this matrix, I only have to deal with the cofactor of that entry here. And so basically, I can reduce this to a 3x3. And then, so I claim this is negative the determinant of Now, in the first row, we get 1, 0, 1, 1. Excuse me, 1, 0, 1. In the second row, we get 2, 1, 1. In the third row, we get 0, 1, 1. So we went from a 5 by 5 to a 4 by 4 to a 3 by 3. And then if I take negative 2, row 1, add it to row 2, and I'm going to put that result back into row 2. When I do that, I get negative the determinant of 1, 0, 1, 0, 1, negative 1 for the second row, and then 0, 1, 1 for the third row. And then last step, I'm going to take negative row 2, add it to row 3, put the result back into row 3. And so I get negative the determinant of 1, 0, 1, 0, 1, negative 1, 0, 0, 2. And I'm done. So this is negative 1 times 1 times 2. Correct answer should be negative 2. That's how we do. This was number 13. And that's a good stopping point for this video. This is a video from section 2.2. We looked at problems 1, 2, 3, 5, 7, 9, 11, and 13. Thank you.